This lecture will be held by Marian Marinov, and it will be on the topic of preventing CPU side channel attacks with kernel tracking.
Thank you. Before I start, how many of you have heard about CPU side channel attacks? Okay, so good that I prepared more of the architectural side of this so you can understand what is a CPU side channel attack. So first, who am I? I am Chief System Architect of SiteGround since 2004. I'm System Administrator for 22 years now. I'm organizing a few events in Bulgaria. I'm also teaching network security and Linux system administration in Sofia University, and I'm also helping with the video team of FOSDEM. So let's start with what we have as a CPU caches right now. We have 4 different caches in the newest architectures that we have. In a single core, you would have layer 1 cache, that is the fastest cache, and it is separated in 2 parts. You have the instructions, the CPU instructions are cached, and then you have the data for these instructions also cached. Then you have the layer 2 cache that keeps the data before it enters layer 1. And you have the level 3 cache that is shared across all of your cores. So when you have a multi-core architecture, CPU that has multiple cores inside of it, you have these caches here. And layer 2 cache is shared within a single core, but you have to keep in mind that most CPU architectures currently support in a single core to have multiple threads executing in parallel. So this means that layer 2 cache is also shared between these threads. The only cache that isn't shared is the layer 1 cache. So we actually have in newest architectures, we also have layer 4 cache that is beneath the layer 3. All these caches that we have are because getting data from memory to the CPU takes a long time. And by a long time, I mean tens of CPU cycles. This means that if you have an instruction that is waiting for its data from the memory, it would take like 10, 15 CPU cycles to get that data, and you shouldn't stop the CPU because you're waiting for the data. This is why you have the caches that cache the data, and when you need it, you pull the data from there. So layer 1 and layer 2 caches can be shared in hyperthreads. Layer 2 caches are shared between different parts of the core, like arithmetical logical unit, fuse, multiply, add, and so on. You see it. And layer 3 caches are shared across all cores on a single CPU. This is the AMD bulldozer architecture. It's an old architecture. It's not the Ryzen, but I didn't want to copy that picture. Here you can clearly see that you have integer instructions. Here you have integer cluster and integer cluster. These are 2 units that can execute integer operations. So integer instructions go there. You have floating point unit here that is executing only floating point logic there. So only floating point instructions will go to this part of the CPU. You have everything you see here is a single core, but on this architecture you have multiple cores. So what you can see here is that we have a branch predictor here. And what is branch predictor? Let's say you have an if statement in your code. That if statement is pretty simple. Either it evaluates to true or to false. But if it is true, you would have like 10 lines of code inside of it. If it is false, you would get only 1 line of code in the else clause. So what you can do is actually execute both the true path and the false path simultaneously, and whichever is actually true, if the statement was true, you would get the result directly from the decision that was taken. So the branch predictor is a part of the CPUs that predicts if this statement, this particular sequence of instructions will go inside the if or in the else clause of your if statement, which is very interesting part, and we'll reach a branch predictor later in Meltdown and Specter attacks. So you have instruction fetcher. This this part of the CPU actually gets your instructions and converts them into a different thing. I'll explain in a bit. All of these instructions go to the pipeline, and this top part of the CPU here, actually this here is sequential. This is fine. You know that everything is executed in order there. After you get all of your instructions into the pipeline, you get an instruction decoder that gets your assembly instructions or machine instructions and converts them to something called microoperands. These are different types of instructions that only the inner part of the CPU understand. And after that, everything can be executed out of order. This means that something that requires data can be reordered later after, for example, in the if statement you get like 3 lines of code. After these 3 lines of code were executed, then you get the data for the if statement itself. This can happen, and it actually happens a lot in your CPUs. So this is the basic architecture. This is basic. It's a little bit more complex than this. So we have 2 side channel attacks that are pretty old. They're from 2009 and 2011. Flush and revolt and flush flush. What are these attacks doing? First, flush and revolt require. Anyone here knows flush and revolt? Perfect. So you get your code, but if all of your applications are compiled with all the data inside of them, with all the libraries, you would get binaries that are huge. This is why we have shared libraries. So shared libraries are nice because you load them once in the memory, and the kernel, the operating system, actually knows that this is a shared library and doesn't duplicate the memory for this. So you get this shared library loaded in the memory, and after that, you execute another binary. The other binary loads the same library. It is with different virtual memory addresses, but the physical memory address of the library is the same in memory. So what you need to do is get this library into the CPU cache. We'll use the last level cache or layer 3 cache. And because we are constantly executing our binary, it will stay in the CPU cache for considerable time. After we find where this shared library resides in the memory, we need to check the access time to this actual memory. So this is our library, the red dot over there. You actually load the binary and you get the library inside the cache. Not the whole binary, but actually the instructions for the functions that you're interested in, and you find them in the cache. So after that, you want to execute this. And for example, these are integer instructions, and they go to the integer part of the CPU. And then what you get is you can time how much time it took the CPU to actually execute these instructions. If the data was in the cache, the instructions will take less time in the CPU, less CPU cycles to execute, because you already had the instructions for this library in the CPU cache. But if they weren't there, you would actually wait for the instructions and the data for them to come from memory inside the CPU cache, which is simple and obvious. But you have a function instruction inside the x86 architecture that is called cache-wine flush. What this means is that you can clear all caches related to memory region. So you can say, this is my memory region, and I want to flush all the caches inside the CPU that are related to this memory region. So you can flush this, and essentially, since you know the memory region, after you flush, you can time how much time it took the CPU to get the data back to the cache again. Timing this would actually tell you if you get what types of bits you get there, ones or zeros. You have to know the actual code that is in memory to perform this attack, but it's pretty easy to achieve and doesn't require any root access. These instructions are all user space instructions that you can execute. You can either write them directly in assembly or write a C++ code that does this for you, and you're timing this information. With the newest side channel attacks, you can actually do this in a browser on this machine and write the code in JavaScript and time it. So it works. So this is force and reload. Every time you have to force the cache and then execute again the application. And when you are executing this application, you would check the memory region again for this data. The next level is flush. It's almost the same attack, but this time you don't need to access the memory. So with force and reload, at certain points you would get cache miss. And CPUs, currently all CPUs have performance counters inside of them, and you can actually count how many times you got a cache miss. So if you try to address the attack and detect it by simply checking for the cache misses, you're not in luck because someone would simply switch to the next attack 2 years later, flush, which only requires for you to flush and flush again the caches. You're only observing the time it takes for the CPU to execute the code in the first. Let me start again. With flush, you have the same shared library, you load it directly, but instead of checking the memory, if it is there, you're simply checking how much time it takes for the clear cache line flush command to execute. If the cache is actually full with data, the CL flush instruction will take longer than if it is already empty. So you don't need to access the memory at all. You simply clear the cache, and you can clear the cache from within different process, and you can time the clearing of the cache in different process, in different user on the same machine. So these are flush and reload and flush attacks. Any questions here? Because I think some people don't understand it. Okay, I'll take questions later. So we flush the data, yep, flushed again. So both of these attacks required CPU flushing. But flushing the cache is instruction that you can actually check how many times it's executed. And you currently have two flush instructions, CL flush and CL flush opt. And the other side, the other possible attack vector here is not flushing the cache, but filling the cache with data that you already know. So this is related only to flush and reload. If you flush the cache with data that you already know, and you load other data there, you don't need to force the cache. You need to simply check if your data is not there. If it is not your data, then other data is on the same, in the same memory region. This is actually used in the Specter attacks. So in January, this talk was started in January simply because in January two very annoying for CPU guys attacks came out, Meltdown and Specter. And the problem is not big for people with desktops, but it's big for people with servers, and especially for people like me that run a lot of software that is not their own. So let me explain more about Meltdown and Specter. The idea was that you can use speculative execution. The side channel attacks Fush and Revolt and Fush that I was talking about are only for the cache of the CPU. They're, let's say, memory related. But the CPU, as I started to explain, can execute instructions out of order and also can predict what will happen at certain point in your code. So your code, as you wrote it, for example, in PHP, converts to actual instructions, CPU instructions in the CPU. These instructions can be executed out of order, and this is because the branch predictor can be taught to actually predict wrong. So the branch predictor, the first branch predictors, which were like 20 years ago in the CPUs, they were simple, very simple statistics. If the past, for example, 20 instructions always evaluated to the if calls, will go this way. If the past 20 instructions always executed the else calls, we'll predict that the next time we have these 20 instructions, we'll go to the else calls of your code. With the newest CPU architectures, you have, for example, AMD have neural networks inside of their CPUs just to predict the instructions, the outcome of these instructions. Intel have more complex logic for predicting the branch, the correct outcome of the branching. So different architectures, but the same thing. If you have a lot of executions of the same thing, you can train the branch predictor to mispredict the actual execution. This is not a security problem, simply because at the end of the execution, the CPU will check if this was the correct prediction, and if it wasn't, it will swap the results. This is not a problem. The problem is that since we mispredicted the result and we executed the wrong path, and in the wrong path we actually pulled data that we weren't supposed to pull, and we pulled it inside the cache, the last level cache, the layer 3 cache. What happened was let me go back to the architecture here. So since we have this data in the last layer cache and it is not removed from there, it's not removed because this was misprediction and we don't care about this data. It will not go to the user, it will not reach the user, but it stays in the layer 3 cache. And this is why I started with the Fush and Revolt attacks, because if you have something in the cache, you already have attack vectors to read this data from the cache. So combine the reading of the cache and this misprediction, and you get a possibility of a process, a normal process, normal user space process, to actually read any data inside the memory, any data. Which is very annoying for people that run other else's code, because obviously when you don't control the code, now you cannot fix the code, and this code actually can attack anything on your machine. It can read your SSH keys, it can read passwords, it can read credit cards, and stuff like this. So the branch predictor can be trained. misprediction actually causes the CPU to execute the wrong instructions. The instructions will end up in, for example, the FPU or the integer cluster, and these devices will actually call for the data, and the data will be stored in layer 2 and layer 3 caches. Okay, so the other thing is that, as I said, most of the modern architectures have multiple threads on the same core. These multiple threads are not other cores, so they're not the same thing as a real core. But what happens is, for example, you have one floating point instruction that is executing this way. It is going through the floating point unit, but at this point, the integer unit is free to execute whatever you want. So if you have instructions that are not all floating point or not all integers, you could actually execute multiple threads at the same time, and this is multithreading. So you have to know that most of the new CPUs actually have 8 or more integer clusters or integer execution units, and have 2 or more floating point units. Everything below Haswell for Intel, for example, or everything older than 2 years for AMD has only one floating point unit, but has multiple integer units. For all the new instructions that you have, SE, AVX, and so on, you'd have other units inside the CPU that can be used for this. This means that you can, in the same time, execute AVX instruction, integer instruction, floating point instruction in the same CPU in the same cycle. So this means that you would essentially have 3 threads. But this is softwarely bound to 2 or 4 threads per core, depending on the marketing of this chip. This is software change for the same chip. So you get this multithreading, but in this case, the integer instruction and the floating point instruction will share the same cache. And since you have multiple integer execution units, you could have multiple integer instructions that are requesting the same cache, so executing the first and revolt attacks on the same cycle while you're actually getting the data, mispredicted data by Meltdown. So Meltdown, most people decided that they will simply fix this problem by unmapping the kernel memory from the user space. Currently, okay, let's not say currently, but like before January this year, both Windows and Linux shared the memory. This is the memory space that you see here. Shared the memory between the user space and the kernel, and you actually could see the mapped kernel pages inside your process. You simply didn't have access to them because you require ring 0 access to this. So you could see the addresses, but you cannot access them. So the protection was that we will split this. Okay, we'll split this and we'll leave a few pointers inside the user space that can be used to access the memory, but through system calls. Which means that before we splitted the memory, when we execute a system call, we could leave the data inside user space memory, and the system call would have an address that is actually reachable from kernel space inside user space, and you won't need to copy this data from user space to kernel space. You simply need to have the correct address. With kernel page table isolation, or KPTI, you actually split this, and you need to have a syscall that will actually copy your data. Since now you're introducing copying of data, this is actually slowing down your processes. Simply because every time that you're requesting the kernel to do something for you, you would actually need to copy the data to the kernel first. Meltdown actually can be exploited by using flush intervals or flush, and you also need transactional instructions. I'll talk about them in a bit. You can use either transactional instructions, or you can use a process that you spawn, and it will die because of the misprediction. It will die with segmentation fault because it tries to access memory that it should not access in first place, and the kernel stops it with the segmentation fault error. However, the CPU already got your data in the cache, and the parent process simply checks this cache info and gets the data. It's a very nice attack, and it's pretty genius and nice and simple. The problem is that most programs actually don't work this way. So you don't have a program that spawns a child and the child's main purpose is to die. You don't have programs like this, or most of us don't write programs like this. So this is an exceptional behavior that you can pretty easily observe on the machine. If there is a process that is constantly spawning processes that die, there's something fishy here. And instead of splitting the kernel and user space memory, you can actually try to detect these events and protect your machine this way. However, this is not a perfect solution. First of all, you still have at least one child process that will die. This will leak around 4 kilobytes of data. So you can leak 4 kilobytes of data before you actually detect this and stop it. Even if you manage to stop it the first place, it dies. In order to make Meltdown work better, you actually have to schedule the child process on the same CPU where the parent is, because this way the parent can access the same cache memory. If you don't do this, on machine with multiple cores, and I'm not talking about laptops, or I'm talking about machines with 20, 40 and more cores on a single CPU, it's a little bit more tricky to actually trigger the same thing, because the misprediction will happen every time on different, the branch predictor that you're accessing will be, not every time, but a lot of times would be on different cores, so you would be actually training different cores, not your own core that actually can detect this. So in order to be more effective with Meltdown, you actually have to issue one syscall, and it's in Linux it's called set affinity. You actually have to pin your child process on the same CPU where your parent process is. Cache wine flush instructions are user space, they are not privileged instructions. However, setting affinity of your CPU, of your process to another CPU is privileged operation. It requires the kernel to do something for you, and it requires a syscall. In the kernel, you actually can grab this syscall, check it, and decide what you want to do. And I'll explain a little bit more about this later. The other thing is the Specter Attack. The Specter Attack was similar to Meltdown. However, it works inside the same process, only inside the same process. This means that it can attack things like, for example, MySQL with stored procedure, or your browser with JavaScript. So on the server, you can use it. Okay, if we use SQL injections as the previous talk was talking about, we can use SQL injection to actually generate Specter Attack on the machine with the SQL server. On the desktops, it's usually JavaScript that is used. The idea is that you would need a code that is called, it's called a gadget. It's a simple if that after the misprediction has a request to an array, and you have the value of this array. So, for example, if you want the second part of the array, you would need value 1 there. And if you have this one in a variable x, and this is the x that you're evaluating in the if statement, what you get is a code that can be mispredicted. And if misprediction is wrong, it will die. But in this dying, it will get the data because the array request for this x would be actually handled by the CPU, and you would get the data for this value inside the cache. You would get the data inside the memory space of your current process. So for me, this is not a big deal because I work on the server side. However, it's still a problem for a lot of applications that execute someone else's code inside the context of the application. So there is a solution, at least in Linux and Unix environments. You can use something called return-oriented programming, or inserting the results at the beginning of your function instead of the end of your function. So your results have to go there in the beginning, and you have to turn back there to get this data. And this way, this simple if that I explained simply breaks because your instructions that go to the CPU are not executed in the order that you require for them to be mispredicted. So in order to fix Specter Attack, you actually have to recompile all of your software that you are running on your machine with the rep2wine protection. The other protections, if you don't want to fix your problem inside the code, you can actually use Microcode Updates from your vendor, from your CPU vendor. And these Microcode Updates introduce these new features of the CPU. Indirect branch restricted speculation. What this means is that if you have a speculative execution, it would be restricted within the same core. So it can be used on a hyperthread. Hyperthread can be used to mispredict something. The predictions would be actually limited only to the same core, but will be shared between threads and hyperthreads. If you move this a little bit more, the second is single thread indirect branch predictions. This means that you're now limiting these predictions to be handled only inside a single thread. And indirect branch predictor barrier is the whole thing is actually every prediction you are essentially preventing predictions from happening. So all three of these are removing performance improvements in your CPUs that were hard to get, and you're actually moving backwards with the CPU architecture if you're introducing any of these inside your CPU, because the performance will drop simply because you can now you can, if you're using only indirect branch restricted speculation, you're actually limiting the branch predictor to this core. And inside this core, you're not using anything, any data information that you can have from other executions on other cores. If you're using on a single, the protection on a single thread, you actually get the other problem that on the same core you cannot share predictions. And if you simply remove predictions, it's obvious. So, yeah. With preventing predictions, you actually prevent user space predictions to leak inside kernel space at all. On every context switch, you now have to do predictions again. All of these protections, separating the kernel memory, introducing these limitations, they cause different performance problems. And this is a benchmark from last week from Phoenix. They're testing the Linux KPTI kernel. a lot of the things that don't require the kernel to take part in your execution, they're not affected by KPTI. Simply because if you don't execute syscalls, your code is staying in user space. If you're staying in user space, you don't need to copy anything to kernel, and you don't have performance overhead for this. But anything that requires a lot of I/O, a lot of networking, a lot of synchronization, this actually gets to the KPTI problem. This is why I purposely took only this snapshot from their research. You can see the benchmarks on their site, on the link down. But you can clearly see the difference here. With KPTI off, you get a little bit more operations than, not a little bit, but you can get 5 to 15% better performance without KPTI. So this is 5 to 15% is not a big deal. Wait. Okay, 5 to 15% is not a big deal for most people. But if you have like hundreds of servers, or in my case, thousands of servers, 5 to 15% would actually get you to a very annoying number, and a number that will translate directly to buying like 100 new servers, simply because you're changing the kernel with one that has protections for you. So yeah, the number is pretty ugly when you have a lot of machines. If you have like 10 machines in the office, you don't have a problem. So what others did to protect themselves from Meltdown? Most of the people resorted to monitoring and analysis, and only 2 other companies except SiteGround actually wrote something on this. Capsule8, they wrote on January 5th. The Meltdown and Specter attacks were public in on January 4th. So on the next day, they released some information how you can actually detect this. Endgame, they shared their research without any code, but they shared some research on how you can detect those attacks. Unfortunately, at that time, I didn't found about their solutions, so we started developing our own in SiteGround. So a few days later, I found about Capsule8 and Endgame, but you'll see the difference in approaches. So Capsule8, it's an open source project. You can get their code. They decided to simply check if there are page faults, so memory misses, in kernel space. This doesn't happen so often in kernel space. The kernel is well ordered and shouldn't have situations, or at least the kernel programmers try to optimize to get the most of the CPU, so they try to avoid cache misses as much as possible. So triggering a page fault inside the kernel is not so often. And you can actually detect this with the perf counters of the perf tool of the kernel. And these are the counters they used: operate, result access, and the main that they were that they based their check on is result miss. So the result of the operation was miss from the cache. So the problem for this is that they're trying to check if there is a cache miss. This will be okay if everyone was using the proof of concept exploits with Meltdown that rely upon push and reload. But as I showed in the beginning, you can simply replace push and reload with push, and you no longer get the page misses. And your detection is not working anymore. The other thing is that with this you can actually only detect the process, but while you're detecting this process, a lot of CPU cycles will, it will take a lot of time, CPU time. And while you're detecting this, the exploit is actually pulling data from your memory. So you now have to decide what to do, and Capsule8 doesn't provide you with decide mechanism. You have to decide for yourself what to do. For example, you can kill the process. But if this is an exploit, if you kill it, they will simply start it again. So the other thing was the endgame research. They provided a lot of insight about the performance counters of the CPU, the performance monitoring unit of the CPUs, PMUs. These statistics, they measured them and they show actual results. You can read their blog post there. The countermeasures here are the same. Endgame and Capsule8 wanted you as a developer or system administrator to decide what to do with the detected attack. However, they don't tell you that it takes a lot of time. Yes?
So would modifying CL flush instructions help in migrating that?
So the question is modifying CL flush instructions will help?
Yeah.
Give me 2 slides. So what we did was, instead of we're using the same thing. Yes, we are using the counters of the processor monitoring unit. However, in the beginning, since I didn't know that the cache counters were already available in perf, I wrote the same all the code in assembly and put it in a kernel module and got the data from there. Afterwards, as I spoke with other kernel developers, I found out that I'm stupid and perf has all the things that I need. We introduced the perf counters inside our code. However, the perf counters were not great. As I told you, flush is a bit problematic. So we decided to attack the attack and simply detect when there is a process that spawns processes that die constantly, and count all the segmentation faults, only the segmentation faults. So we changed the task struct of the kernel and added one more field to count all the childs that died with segmentation fault. When we detect such a process, which is detected on every reschedule of a process, so this is exactly after the segmentation fault, we already know that there was a process that had a child that was that already died with segmentation fault. So we stop this process. We are not killing kill minus kill. We are kill stopping it. So essentially, we are pausing the process. But when we are pausing this, we know that the user that started the process has the ability to send cont and to continue this process. So we changed a little bit the logic of kill, and now you cannot send a signal to continue a process that was stopped by our implementation. So only the root on the host machine can actually kill this process. The user can see the process that it is in D state, that it's stopped, but you cannot continue it. We also log that we have stopped this process, so we know the user, the process ID, the actual command, the path to the command, and we can inspect the command or suspend the account or suspend the container. So on our infrastructure, we are a shared hosting company. We have a lot of accounts on a single machine, but we also have other machines with a lot of containers that have root access inside of them. So these guys have root and they still cannot kill their process. This was our change, what we did. This was to prevent this from happening, from leaking a lot of data. CPU pinning, we simply changed the set affinity to report to the user that it did the change, it did the pinning, However, it doesn't do anything for the user. CPU pinning is available only for the root of the host machine and nobody else. This is because we need to pin the CPUs in the beginning when we start the machine, and after that, after the machine has booted and it is configured, we don't need to change anything on the CPUs, how they are arranged. So the user, he's running on a shared environment. These are the limitations that we provide, but it's still quite good because now Meltdown is pretty hard to execute without the pinning. Now, then we decided, okay, we'll go to the CLFush and CLFush opt, and if we limit them, we will effectively stop both Fush interrupt, and essentially we will stop Meltdown. However, since they're user space, I can write an assembly, compile it, put it on your machine, and it will execute my instructions. Simply because they are not privileged instructions, it doesn't require to go to the kernel to execute this. It's not like a set affinity which required a syscall. So the other thing was our kernel developer found that even if you tackle the problem with the CLFush and CLFush opt, the cache can be implicitly flushed when there is an invalid instruction in your code. You simply write an invalid instruction, compile it without a care that it's a wrong instruction, execute this code, and your application will die. That's not a problem because it will clear the cache. So you will not be using CLFush and CLFush opt, and again you will be fucked. Yes?
So regarding the accuracy, which one is more accurate? Flush plus reload or flush plus flush?
About the accuracy,
And why?
About the accuracy, I would say that a flush and reload is more reliable simply because you get the actual data. You're not assuming anything like with first flush. Yeah, with first flush you are assuming things and you are detecting timings. If you read the papers, I have linked the papers at the back and at the final slide of my presentation. If you read the papers, you would see that there are actual time charts that both first flush and first interrupt generate in order to detect which symbol you have in memory right now.
That's the reason why flush plus flush is way faster than flush plus reload, right?
I don't know which is faster actually. I have tested both, but I simply don't remember if there is a significant difference in the speed of them. Flush is faster simply because it doesn't pull data. It checks only timings. But on my machine, it wasn't significantly faster. In the research, it says that flush is a lot faster, but I can't tell you anything about this. So we decided to try to trap those instructions, CLFush and CLFush opt. However, trapping those, since they are unprivileged, is not possible. There is no machinery inside the CPU that will allow you to trap an instruction that is unprivileged. So then we started thinking about what if we start the process and we don't read the whole process binary, we read only the instructions it has and detect if there is an instruction that is CLFush or CLFush opt. In this way, we can implement detection if there would be an implicit flush by seeing that in the code there is an invalid instruction. This, however, is slow, simply because you have to execute the actual code, and in parallel you have to execute the detector. Or it can be even slower if you check each instruction, if it is CLFush or if it is invalid instruction. So direct checking, we simply scratch that. Inspecting the binary for in parallel, we're still thinking about this. And there is another solution, virtualizing the system in QEMU. So your whole machine gets inside the QEMU, and the QEMU can get you the requests you get for CLFlush and CLFlush opt. You would get them inside your host machine, and you can trap them via QEMU. Essentially, QEMU is doing the same thing when it is emulating different options for the CPUs. So when you, for example, start a KVM, you can say that it is 32-bit CPU, even though you're running on a 64-bit architecture. It can say that this CPU supports AVX or doesn't support AVX. And this is by capturing one pretty neat instruction, CPU ID, that returns a binary bit stream, and in this bit stream, every bit decides, do you have this instruction or not? Do you have this functionality or not? So you get this inside, you capture this inside QEMU, and instead of returning the actual result from the CPU ID instruction of the CPU, you get this data and filter it or directly wire to the VM that it has only these functionalities. That's it. So it's possible to do something about it in a virtualization, into a virtualized environment. For people that are not kernel developers, they may be tempted to add the no CLFlush option on the kernel line when you boot your kernel, and would think that this will simply remove the CLFlush functionality. No, this will remove the CLFlush calls from within the kernel, but only from within the kernel code. Every user space application will still be able to execute CLFlush. So don't do this. Don't do this. There is no reason to do it at all. Events that you can monitor from with perf, you can monitor the demand clean. This is actually an event that is fired every time a CLFlush or no or CLFlush opt or implicit CLFlush is called. So every time the cache is cleaned, you get an event. So you can monitor for this. You can also monitor for layer 3 cache misses, last layer cache, the cache that is shared between all cores. You can monitor this. And the other things are mentioned in in both Capsule8 and Endgame research. The operate, result access, and result miss. The other thing that I didn't tell you about is the transactional synchronization extension of Intel. It's a nice way to actually synchronize multiple threads inside your application, but instead of synchronizing them in the kernel or in user space, you can actually say to the CPU, synchronize these, execute these instructions, and either finish the execution for all of the instructions or return nothing. So this is executing a transaction of instructions inside the CPU, which is very nice. But before Haswell, inside Haswell, you should have these disabled because there is a hardware problem. There is an errata for this, and you should have already patched your CPUs with the microcode that is removing, disabling the TSX instructions. However, these are available in Skylake. So if you have newer CPUs, you have these instructions, and somebody could use, instead of creating a process that will segfault, these instructions, the parent can issue transactional instructions inside the CPU that would be mispredicted, that would be removed from the CPU. However, you'd still get the cache filled with the data that you want. So TSX instructions are bad for, there is almost no software that uses them. So try to find the microcode that disables those on your Haswell and previous chips. And for Skylake, the solution is you're not going to like it, but you have to monitor for aborted transactions. Because most of the time you wouldn't get software that is using transactional instructions. On your machines, this should be 0, and you can see the counter increasing during attacks. And then, based on this, you have to find the process that actually issued the transactional instructions, and then stop this process. And this is only based on statistics, so you have to write a lot of crappy software to actually do this. Yeah, the TSX instructions are also in user space. This is a big problem again, because you cannot trap them and you are left with the statistics. Relying on CPU counters is not enough, simply because it would take a lot of time to find the process that is causing this and then stopping it. So you can use the same mitigations that we introduce inside our kernel to count this and directly stop it, but now you would leak not 4 kilobytes, but a lot more. I don't have a lot of time, so I'll simply skip to questions. Do you have any questions? How many exploits have I seen on our machines? Since January, 0, excluding our tests on our machines, because we do live testing. Any other questions? Yes?
You were saying you're stopping a process and it can just be killed by the uppermost root. Does this imply that it is possible to attack with the denial of service by exhausting process IDs?
I'm sorry, can you repeat the question?
You were saying that you're stopping the processes and only the uppermost root can kill them now. Does this mean you could, we could attack you now with denial of service by exhausting all your process IDs?
Try. Let's say that limiting is my life and limiting users is not so hard. So there is on shared hosting environments, at least on ours, you have the max process limit first for the user, then you have a control group for that user, and then you have another control group for this container machine, and then inside this container you have another control group that is limiting, and we will still have processes left on the host machine. And so since we are using namespaces for the containers, let's look at the container side where we have an attacker that has bought a container with root access on our infrastructure. He has his own PID namespace, so he can affect only his own container. It is not going to affect the host machine. It's not a big problem. We currently have machines with between 20 and 30,000 processes running at the same time. And it's not a problem, and I have personally tested to 1 million without a problem. Other questions? Yes?
How bad are the 4K?
How what?
How bad is the leaking 4K?
How bad is leaking 4 kilobytes? Let's say that not many people have SSH keys that are 4 kilobytes. Most use 2 kilobyte keys. And this is SSH key. How bad is it? You tell me.
But when you leak 4K, do you know? So the question is, when the attacker gets the 4K, does he knows what he gets, or he needs more data to be able to know or distinguish?
Usually the attacker needs more data, statistical data, to actually understand what he got. However, depending on the memory address from where he got it, and based on the idea that the Linux kernel source is available to everyone, and knowing the version of the kernel, you would actually easily guess what you got from there. If it is a user space memory, then you can try to, without attacking the machine, without actually triggering Meltdown, you can try to see what each library is loading into memory, how it looks like as a memory layout, and again you would pretty easily get the right assumption that this is, for example, from the GNU PG or from OpenSSH or from OpenSSL or whatever. So the libraries are not so, they're not the same as memory footprint. So you could actually very easily find out that if you have this structure in memory, this is a structure from OpenSSL. If you have this structure from memory, this is from Nginx, or this is from OpenSSH. So if you're a good attacker and you already have these statistics on your machine, yeah, you can assume a lot of things about memory that you already got. Other questions? Then, thank you very much. I hope you enjoyed it.